Welcome back, Year 11. This is lesson 7 of radioactivity. Make sure you have completed the starter quiz on Study Zone. So, today's lesson is looking at how to determine the half-life of a model radioactive source. Last lesson, if you remember, quick recap, we looked at how we can calculate the half-life of radioisotopes, and in this lesson we're going to start off by looking at how we can model radioactive decay. Here's the spec. What's highlighted in yellow is what we covered in our previous lesson, and I've also started to highlight parts of lesson 7 because there's quite an overlap between lesson 7 and lesson 6. Notice just here, I've highlighted that in purple because we're going to be doing more of that this lesson to be able to select a suitable isotope for a given application. So for lesson 7 then, we complete in pages 46 to 60, and we're going to start off by looking at the random nature of radioactive decay, which we did last lesson to a degree, if you remember the simulations, using a constant probability, using a large collection of dice, coins, or suitably programmed spreadsheet. We're going to look at first of all coins and then dice. Likewise, I suppose I could colour this in purple and yellow because we started last lesson and we're going to be doing more again today, looking at how to plot or sketch a decay curve for radioactive materials. Okay, let's get on with today's business, and this is it. Determine the half-life of coinium. There's an element of humour there, because where you have a radioisotope like uranium and iridium and so on, the elements finish with an IUM. Yes. So what you're going to be doing is looking at a video where Mr. Hancock has kindly modelled this experiment, done the experiment I should say, and we can then plot our results in this table underneath. Okay, so we're going to watch the video now, and if we quickly look at the procedure beforehand, what you need to do when you're watching the video is to count the number of 2p coins, record the number in the table as I just showed you, and repeat for subsequent throws. You can pause and read through that. I don't need to read through all that. And then you're going to plot a graph of undecayed coins. Just remembering all along, why are we doing this? We are using coins to model the radioactive decay. More on that later. Let's watch the video now and take some readings. Okay, so what we've got here then is 52p coins, and Mr. Hancock has raided his piggy bank and put some temporary white marks on the coins. If you look really close, you can see that those coins that are facing tails up are marked white. Those that are heads up haven't been marked. The white marks are on there just to help you see. So each coin represents an atom. If the atom is if it's undecayed, then it's heads. So what Mr. Hancock is doing here now is collecting all the atoms that have decayed and put them to one side. Now if you think about it, on average, if you throw 52p coins down, you'd expect half of those 2p coins to have decayed. Let's just see. And what you can see here then is the number of coins. Mr. Hancock is just going to count them all up and put them in rows of 5s to help you record in your table the number of decayed 2p coins. Okay, so if we were to count the number of 2p coins there, you can take each row 5, 10, 15, 20, 25, 27, 29 coins have decayed. You now make a record of that in your table. Here's your table. After throw number 0, obviously the number of undecayed coins was 50. So we just write that in the table, 50 coins. 29 decayed after the first throw. That means we have 21 undecayed coins remaining. So we're going to do the same now for 2, 3, 4, 5 until we run out of coins. Okay, what Mr. Hancock's done here now then, he's collected the coins that were undecayed, that were on heads, put them back into a pot, give them a shake, and throw them into the tray again. What he's going to do now is collect the decayed coins and add them to here, and then we can record in the table what we found out. Go back slightly, and then we can see there's 2, 4, 6, 8, 10, 12. Just roll it on slightly. So if 14 coins are decayed, then there must be only 7 coins left that Mr. Hancock has just picked up now and ready to throw again. Going back to our table, what I just said, if I show it a different way, we had 21 undecayed coins before Mr. Hancock just threw. 14 of them decayed. That means we have 7 coins remaining. So what we're going to do now is the same thing. Throw the 7 coins and see how many are undecayed. So you can see out of the 7, 3 have decayed and 4 remain undecayed. So we'll make a note of that. Right, so we just write 4 there. So you can see only 1 more decayed, 3 undecayed. See, 2 decayed, 1 undecayed. So, all Mr. Hancock's done now, he's thrown that last green. Let's go off the tray. Ah, there is landed. What is that? Is that heads or tails? We'll class that as tails. Or that. Okay, when he threw it the 6th time, there was a slight mark on there, but it was heads, so we still had 1 coin after 6 throws, and on that 7th throw, it decayed. There's our table of results. Your task now is to plot a graph of number of throws against number of undecayed heads. Axes have been drawn for you. You need to use now an appropriate scale on both the horizontal and vertical axes, and then I want you to work out the half-life of coinium, 2p coins, and write in here what you think a half-life is. Remember, half-life is we usually say the time taken. We are changing from time taken to the number of throws needed for the coins to reduce to half their original value. Okay, pause the video now and plot the points, draw the curve of best fit, and write your answer in I'll just use a highlighter in this area here. Okay, so pause the video now and then plot the points from the table onto this graph. When you've completed that, press play again. I made a quick start. I'm at the 3 throws, so I'm just taking these points here. So after 3 throws, we're on to 4. I'm just looking for 4 on the Y or vertical axis. 4 throws, number of undecayed is 3. 5 is 1, 6 is 1, so you write down here, look, 6 is 1, and then 7. 7 is 0. Okay, now what you need to do then, of course, is draw a curve of best fit. So I'll just select a different colour pen. You use a pencil on your booklets, and then I'll just, as best I can, draw in a curve of best fit. It's okay. It's a bit uneven between the 0 and the 1. Okay. Now, what we're looking to do here is find out what's the half-life of these 2p coins, or coinium as they've been coined. Well, what we do, of course, we look to see what's the original value. 25, 50, half of 50 is 25. So we go down to 25, there's 25. Get your ruler, extrapolate from the line with the ruler, and actually I'll use a different colour so we don't confuse the curve of best fit with the lines of extrapolation. And I would say, I'm going to zoom in a little bit more. I would say that looks as though it's 0.8 and 0.9. So I'd say 0.85 actually. Sorry, 0.85. I would put that down as the half-life of coinium. Now, coins aren't radioactive. That's fair to say. But what we're trying to do is look at the analogy between coins and radioactive atoms. We wouldn't be, for radioactive atoms, the equivalent of the number of throws is time. The time could be seconds, minutes, years, but it's a way of trying to help you understand how decay works, how it's a random process, and that there's a certain probability that each coin, the probability in this case of each coin becoming decayed is half, 0.5 for each throw, or 50% chance. Another way of modelling radioactive atoms, and this is the example from the GCSE specification, is to use, well, let's read it. Determination of the half-life of a model radioactive source, for example, using cubes or dice. And I've highlighted the important words here. It says radioactive decay is a random process. The number of radioactive atoms present in a given sample will halve in a fixed time period, depending on the probability of decay. Now that's what I want you to think about. The probability of decay for a coin for each throw is half, or 0.5. And you would have learned, or will be learning, about probability in maths or numeracy. For what we're doing for dice, if you look at the dice here, you know a dice is it's a 6-sided shape, or cuboid, or cube, actually, because all the sides are equal, and one of the sides is shaded in. Therefore, it's a probability of 1 in 6 decaying for each throw. The methods there, I'm not going to read through it. You can pause and read through it. But I am going to fill in this table because Mr. Hancock again has very kindly filled himself throwing these dice into a tray and then counting the number of decayed and undecayed. So I'm going to just show parts of the video, fill in the table, and then importantly compare the half-life for dice compared to coins. What I want you to think about though, think. Will the half-life of dice be larger or smaller than coins? Think about coins, think about dice. Which has the larger or longest, perhaps a better word because we're usually dealing with time, the longest half-life? And just as a reminder, dice have a probability of a sixth and coins have a probability of half. Okay, what we got here then, same green tray in the background, but this time rather than 50 coins, we got 50 cubes or dice. They've been arranged in sets of 10, so 10 times 5, 50 cubes. And Mr. Hancock now is going to pick these up, shake them, throw them on the tray, and then the ones that face black side up are going to be the decayed cubes. They're going to be taken away and we throw again. Okay, so this is obviously going to take a bit of time. All the decayed cubes being put to one side. If you look, Mr. Hancock's arranged the dice now to the left hand side, and there's 13 cubes that have decayed. We'll add that to the table. Here's our table. So after throw 1, the number decayed at 13, the number remaining are 37. Decayed 13, Mr. Hancock now is going to just pick up and throw the remaining 37, and I'll fast forward the video again. Okay, here you can see then we've got another 7 that have decayed, so the total of 20 have decayed. Let's add that now to our table. And 30. Now, I'm just going to pause there a moment. I think what's happened, if we just go back a little bit, oh, there we go, and I'm going to pause it just there. I think what's happened here, we've jumped a throw because we've got another 8 that have decayed, so we'll add that to the table. What we'll do now is just I'll pause the video towards the end so that we can add all throws to the table. Okay, so you can see now we've got a number of throws that have taken place. I'll pause, rather than you count them all, I'll just add them to the table. As an optional extra activity, what I'd like you to do is just plot this table on a graph and work out the Half-Life, or use Excel spreadsheet and put that data in and use a software to do it instead. It's optional, it's extension work, and I'll be doing it myself in a moment anyway. And I've started underneath, look, just drawing the axes, and I'm going to plot those points in a moment and fast forward this video. Okay, here we go, there's the table, there's the points plotted. What I'm going to do next is draw in a curve of best fit. I've added in now my curve of best fit. So, to calculate the Half-Life, take your original value with 50 undecayed dice at the start. Half of 50 is 25. Go across from 25, see where it hits the curve. Extrapolate, so see where it hits the curve. And we go down from there. So what you can see is the dice have a half-life of, it's in between, if we look at that, this is 3, so it's in between 2 and 3, 2.5 throws. .5 throws. Now, if you repeated that experiment, you'd get a slightly different answer than 2.5. Could be 2.6, could be 3.2. However, the average value would come out as 3 throws, because the probability of landing on that one side of the dice is a 1/6, a 1 in 6 chance. So say if we look at that dice now, I've shaded in one side here, or if you think of a normal dice and you've got a 6, if we look from a bird's eye view, you've got a 6 on one side. What's the chances of rolling a 6 of the dice? Well, it's 1 in 6. And on average, you'd roll a 6 in 3 throws, or that would be what we call a half-life, in terms of half of these dice decaying. If we think of our coin, Well, there's a 50-50 chance, a 1 in 2 chance of landing on the decayed side, the tail. We found is 0.85 throws. Think of that then as a way of trying to better understand the idea that every radioisotope has got its own half-life, and it's to do with this random nature and the probability of each isotope decaying within a certain amount of time. In our model here, we haven't talked about a certain amount of time or seconds or years. We've used the idea of throws, the analogous idea of time. So the half-life of coins would be 1 throw if we did lots of repeat readings, and the half-life of dice would be 3 throws. If we were doing these experiments in school as normal, what we would do, we would pool together the results of all the different groups, and we would get much closer to this 1 and 3 half-life. We're now going to go back up to page 14 of the booklet and look at the half-lives of different elements. Sorry, page 42. So bottom of page 42, if we take a couple of examples, an element with a very short half-life, boron 19, 3/1000ths of a second, half-life. So that means that each atom, the probability of it decaying in a second is far higher than, say, an element over here, such as sodium 24. That's got a half-life of 15 hours, or in terms of seconds, to make that comparisons with the boron 19, it's 53,900 seconds, because the 10 to the 3 seconds there means 1,000 seconds. And remember, the reason for the difference is because of the makeup of the nucleus itself, the imbalance or lack of imbalance of protons and neutrons in the nucleus. Okay, if you can turn on now to page 48, please. It should look like that. Now we're going to use this idea of each element having its own half-life to understand this next topic, which is called carbon dating. You probably would have heard of it. And carbon dating is a clever concept used to work out how old things are that perhaps have been dug up from underneath the ground. Okay, first recap on what's happening when carbon-14 is decaying. It's turning into nitrogen, and we see a nice simulation here with all these 100 atoms decaying to nitrogen, and you can see what should half would decay before the half-life, which is around 6,000 years, and half after. We can show that here as well, showing that the carbon atoms decaying into nitrogen atoms, the red turning into blue. We can increase the number of carbon atoms we start off with, but the half-life remains the same. So the red is the carbon going down, and the blue is the nitrogen going up. If we use our Geiger, remember our Geiger-Muller tube, it reads the level of radiation, and what we read in here now is, if you look at this graph at the top, carbon-14 is 100%, but when the tree starts to die, you can see that carbon-14 will start to reduce, and you can see it reducing here and we should find that it'll go to 50% by the time it gets to 6,000 years. We won't wait another 3,000 years, so I'll just pause and record in a moment. Okay, so you can see now, just under 6,000 years, we've reached the point where there's 50% of the carbon-14 left in the tree. So by working out what percentage carbon-14 we got left in an object that used to live, like a tree, we can work out the age of the tree. So there's been situations where old shipwrecks have been dug from below mud, or human remains have been dug, and we've been able to tell how old those remains are. So if you look at this simulation, you could put the Geiger 2 next to different artifacts that could be dug up from beneath the ground, and it tells you at the top here what percentage of carbon-14 is left. 88.2%. And you go to the graph, 88.2% will be somewhere around here, and you come down, it'll be about 1,000 years. Or then you could go over to this human skull, could be dug up by an archaeologist or a scientist, and say, right, oh look, using our Geiger Muller tube, we can work out that 76% is around about 2,000 years. So if we put 2,000 years in there and check the estimate, then we can see, yeah, it's around about that value. Back to the booklet. What you need to do here is write in, I'll do the first one, you can do the second one, the value of the carbon-14 in both those circles. So for that second circle there, it's going to be 1 half-life. So half of 32 is 16 of carbon-14. Now, just pause the video and complete this one, please. Well, you should realise that after the second half-life, so this is the first half-life, this is the second half-life, then we'd have halved from 16 kilograms down to 8 kilograms. So you would just write that in the circle. Right, next what I'd like you to do is read through the rest of this page in your own time and answer those questions underneath here. So it'll be a self-assessed activity. So I'd like you now then to read the questions and answer underneath. So pause the video now, please. Okay, I won't write down the answers. I'll give you a verbal answer, and you can check against yours. What is carbon dating? Carbon dating is a method of measuring how old something is, and rather say something, a dead organic material, so something that was living. So carbon dating is measuring how old dead organic materials are. Question 2. Why do you think that dating dead organic materials over 60,000 years is almost impossible? Well, if you look at this graph, you can see that the percentage of carbon-14 remaining is very, very small. That looks about 3 or 4%. So you can imagine after 60,000 years, if we were to continue that line, it'll be carbon-14 would be too small to measure. Question 3. The Turin shroud is a holy relic. Reputedly, the shroud used to wrap Jesus in after his crucifixion. The shroud appears to have the image of a man etched on one side of the cloth. In 1988, 3 independent carbon dating labs analysed fibres taken from the shroud and discovered that the sample study contained just over 90% of the original amount of carbon-14. Use the graph to estimate the age of the shroud. So 90%. We go up to the graph, get your ruler, you come across from 90%, wrong pen, come across, and then it's going to be a little bit of estimation here obviously, but you just need to extrapolate a line as best you can, coming down from there. Now if you look at that, you could use a ruler to get a better scale, but there'll be a level of estimation in here. This isn't the best ruler, but it gives us an idea. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Around about 11 marks there, and we're 2 across. So I suppose the best we can do there is, I would say, it's about a 10. It's not far off, say 600, 700 years. I think I'd allow anything between, I think, a wide margin of error here. Allow anything there really from 500 to 1,500 years. Okay, in the absence then of a ruler, I'll try this another way, just using that backing grid paper to show the distance then between the value here, the 90%, that green arrow, and if I use a different colour, and that arrow there. If we just label this at the top here, look, there's 1 square there between the 90%, and then for the full half-life that will go up to 3, 4, 5, 6, just under 7 squares. So to work out this value here in years, we would divide 5,700 by 7, giving you 814 years. That would be a more accurate way of doing it, but in absence of a useful scale on the graph, again, I'd allow anything between those 2 values. Right, that brings us towards the end of page 49. We were going to cover in this lesson as well applications or uses of radioactivity, but I think we've covered quite a bit. We looked at modelling of radioactivity, and we've looked at carbon dating. So what we'll do instead, we'll cover the section on uses of radioactivity in lesson 8, which will be going over some parts we learnt in previous lessons. So that's the end of lesson 7. Make sure you've completed the plenary assessment. See you next time. Bye.